Here we present the work titled Machine Learning for Energy Performance Aware Scheduling, where we use Gaussian process, Bayesian optimization for design space exploration. The project is motivated by the end of Dennard scaling in the semiconductor design, where power consumption constraints all processes from turning on. We therefore try to answer the question of can machine learning autonomously explore the optimal strategy to balance energy and performance in heterogeneous systems. The presentation is divided into 3 parts: 1. Simulation setup, 2. Metrics we care, 3. Emulation of policies and frequency setup. The task is considered as a 5-element tuple, where each attribute defined as in the table. We adopt a multi-core system, among which types of processors exist, including little, medium and large cores. They have distinct frequencies ranges. The task series are randomly initialized following the Poisson process, whose waiting time modeled by exponential distribution. We consider 3 types of schedulers for assigning tasks to processors here. There are also per type attribute, for instance, time quantum, that needs to be tuned. An example result of round-robin scheduler assignment for 6 cores is shown here. We adopt SIMPy as the back-end environment, supporting the different simulation parts. A logging system is used for collecting data, verification, and debugging. The latency metric is the priority-weighted turnaround time. For a task with higher priority, they weight more in the latency metric. The energy and power are derived as in the paper, composing of 2 parts, dynamic and leakage. They are only related to the changing variable frequency. The rest constants are shown in the table. Next, I will introduce the design on the emulator and experiments for Bayesian optimization. As we aim to minimize the energy and time cost of the simulator system, we first define a joint objective function that includes the logarithm of energy and time with weights. Second, we select default environment parameters, like the number of tasks, to simulate a standard scheduling scenario. Basing on this, we also define a search space for tunable parameters, like the properties of cores and scheduling algorithms. Next, we set up with a series of experiment groups. The first group we want to investigate in particular is the selection of kernel, as it reflects the prior knowledge on the optimization landscape of this problem. The results suggest that Matérn kernels achieve the best results. This indicates the non-smoothness of this problem. Therefore, we select Matérn 2.5 to conduct the following experiments. Second, we design experiments to simulate scenarios with different focuses. We change the weights from the objective function to simulate energy-first and time-first tasks. Specifically, the results for energy-first setting suggests a very interesting strategy. We previously assumed that little or medium cores may play important roles here. However, the model actually explores race to idle, where it uses a very powerful setting with big cores to complete tasks as soon as possible, and save the energy cost eventually. Additionally, we simulate the scenarios with different workload pressure. High lambda rate means high pressure. We also notice that the model obtains interesting configuration under extreme setting, as there are only one little core and very low frequency. We assume the reason is the extreme pressure leads to a nearly impossible time cost to be optimized. Thus, model decide to set the cores with minimum energy cost and try to satisfy the optimization goal apart from time. Finally, we present the experiment that optimize time and energy costs as 2 distinct goals. This gives us a Pareto front includes a series of optimal configurations. The left figure indicates the Pareto front is a curve instead of a single point, which means the goals are conflicting and there is no dominant configuration to satisfy both of them. The right figure explains the reasons behind confliction. The important parameters for those 2 objectives are actually very different. In summary, in this project, we explore how to deploy machine learning methods to explore an optimal settings to balance between performance and energy in CPU scheduling tasks. To this end, we first design a simulator for heterogeneous CPU scheduling. Next, we introduce a series of experiments with Bayesian optimization under different scenarios. Our results suggest that the optimization landscape for this problem is rough. Besides, the model successfully discover advanced strategies under specific scenarios. Finally, we found that there is no dominant strategies that could minimize both time and energy costs.